Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students, so we continue with our discussion of the properties of matter and the both the last time we looked at the mechanical properties of fluids, and then we looked at the thermal properties of matter, right? So before, this is as an introduction to all the other material we are going to learn in terms of gases and how gases behave. So let me quickly reintroduce some of the material again. And as I said, you do a lot more of this in chemistry, but you should still learn how the kinetic theory of gases evolved, because it provides you a more mechanistic view of how heat and temperature are related to the mechanistic ideas that we have learned so far. So that you understand the ideas in the small and the ideas in the large are actually related. And this is a very important aspect of a lot of things. Chemistry in particular deals with a combination of the ideas at the molecular and atomic level, all the way to what happens when you have a conglomerate of particles in a free system. And that idea of a system or a closed system is fundamental to our understanding of everything else that you will go on to learn as you study, say, a mechanical engineering or a chemical engineering, etc., metallurgy, etc. So here you look at it a little bit from the physics side and look at it a little bit from the chemistry side, and so you get an idea for both. But actually, there is not like a chemistry science and a physics science. There's only one science. And eventually, there is, if you end up in one of these bioengineering sciences, there also, that's a third aspect of the things that you do learn. And so that all this has traditionally been the science. So so there is only one science, and so in order to facilitate that understanding, to understand this and that and the others. And so, like, chemistry is, like they say, the central science, right? And so it links also, like when you learn organic chemistry, right? They call it organic chemistry because it's of its relationship, close relationship to the bioscience. So it's worth noting here, as I go about explaining this, also, that the idea of the DNA, the idea of the DNA was found not, did not originate in a biologist, although we all know that Watson and Crick made the model for the DNA eventually, and it led to our modern understanding of what is at the heart of life. Okay? The idea of DNA, right, originated in a paper by Erwin Schrödinger. Professor Schrödinger had originally a German, left Germany during the Second World War because of his ethical concerns with what was happening, and he moved on to Ireland, or he moved on to the British Isles. Now, there, towards the end of his, otherwise, or not otherwise, towards the end of what was a stellar career in the sciences, Erwin Schrödinger wrote a paper called "What is Life?" It is available on the internet, and I welcome you to all to read this. Now, why I bring this in is that he worked at the smallest of the smallest levels when it came to science. He is best known for H psi equals E psi, which is the Schrodinger wave equation. When you learn quantum mechanics, perhaps the first thing you will hear about is Mr. Schrodinger and his cat. But yet Mr. Schrodinger or Dr. Schrodinger, Dr. Schrodinger um, went on to pen what is life, and both um, Watson and Crick, you know, attribute their search for the idea of what is life, of the idea of DNA, and their eventual success in that forum of finding what is DNA to Schrodinger. you know and so Schrodinger's the mark that Schrodinger left in our world in terms of our understanding of it is phenomenal. Having given you that introduction, let me go back into heat and temperature. Heat and temperature have to be understood both in the small, in terms of the laws, and in terms of the statistical aspect of how the small and the large converge. You know, heat is a form of energy. In fact, it is the form of energy that is transferred between two systems or systems and its surroundings by virtue of a temperature difference. When there's a temperature difference, you all know that heat flows from one place to another. As you know, the what dictates this is basically also originates with Newton. There is what is called Newton's law of cooling. The rate of heat transfer is proportional to the temperature between a body and its surroundings. Okay, so it's a differential equation, or a very simple differential equation: dq by dt equals ms d theta by dt, right? Rate of heat, right? So now, as the temperature difference declines, right, you also have the transfer of heat also correspondingly declines. Okay, and therefore it's a time driven equation. Rate is always a time driven thing. So the idea of relating the time driven difference in temperature is related to that. So we then explained temperature, and then we explained the ideal gas equation: PV equals nRT, and as you know, there is Boyle's law and Charles' law, and when you combine Boyle's law and Charles' law and you link it together, your PV equals nRT. Very central to our understanding. The ideal gas equation is very central to our understanding of heat and temperature. Okay, so T in the case of PV equals nRT is in absolute kelvins. That's the most important thing, and R is called the Rydberg, not Rydberg. It's a universal gas constant. Okay, it's not the Rydberg constant. Universal gas constant. 8.31 in 10 to the power of something. So when you apply PV equals nRT, N is the number of moles. So you have a enclosed gas in a volume, okay, and let's say in a system that is, it cannot exchange between in and out. Let's say it's a closed balloon. Okay, now in a closed balloon, right, and you've tied the knot on the top, right? So what is the pressure, what is the volume, and what is the number of moles, and at what temperature is it? These four are intricately related using the ideal gas equation. But the thing is, most gases are non-ideal. Yet we regularly apply ideal gas equation for the longest time when it comes to class 12 and maybe even in your college. When heated, most objects will expand, except we discussed water last time, right? Balloons shrink when placed in ice. Metallic lids on glass jars can be opened by placing them in hot water. Okay, I usually tap, it against like when you have that sealed bottle or something, I tap it slightly to let a little air in. That's why they do that, and then you can open it using your hand. So now length, when it increases, experiences linear expansion. Volume has the coefficients we already discussed, right? How the coefficient of expansion is twice in the case of area and thrice in the case of volume, right? This is, and that is very obvious for anyone who learns calculus, right? And so V is equal to, so linear expansion, L plus delta L equals T plus, L is, dl by dt is a constant, right? So as a result, you have L plus delta L equals, and that constant is alpha, right? So therefore you have this L plus delta L equals, correspondingly, alpha times T plus delta T, and then you have the equation delta L by L equals delta T by T alpha, right? So that is the coefficient of linear expansion. So when it comes to volumes, right? Volumes, the coefficient of volume expansion is 3 times typically the coefficient of linear expansion, right? Why is that? Because you have 3 dimensions. Each of the dimensions is growing, right? So now, with respect to, we also discussed the anomalous expansion of water. Water has its greatest greatest density at 4 degrees. So what happens is, when water is at 4 degrees, it is at the lowest bottom of the ocean. If you just kept 4-degree water, if you put 4-degree water, it should go. In fact, the molecules move so fast that eventually all the water reaches the same temperature. But if you let it go, it should go right to the bottom because it's heavier, right? But then when it increases, right, then let's say it freezes some more, right? Then it comes back up, and then because it expands. Okay, when it's ice, it expands. Okay, so when it's ice, it has that lower density than the cold water, and therefore ice floats in water. Okay, and so the water is at a higher temperature than the ice. Ice is at 0 degrees or more, and then you see this idea of a trough. The maximum the least volume is at 4 degrees, and it's also the point of greatest density. So that is the curve, right? So this is the anomalous expansion of water. Okay. So now, and then we discussed the coefficient, and then we went on to this idea called specific heat capacity. Specific heat capacity tells you that the change in temperature is proportional to the heat capacity. The specific heat capacity is the rate at which the temperature to the heat, that ratio is given by the specific heat capacity, and it is specific to a particular kind of material. So for instance, gold, which is a metal, has a particular specific heat capacity. Iron, which is a metal, will have a specific heat capacity. Like that, each of the materials, it is a property of the particular substance. So dq by dt is, so delta q equals ms delta theta. Okay, and dq by dt is, of course, also proportional to the amount of substance you're using. More material, it will absorb more heat, obviously, right? So ms d theta equals delta q. Okay, delta q equals ms delta theta, where theta is the temperature, the change in temperature. Okay, so as you absorb more, as your temperature increases, right, the capacity of heat also increases. What does that mean? It means that there is a latent heat is a latent property. Okay, so as the temperature increases, so does the heat capacity or the heat absorbed. Okay, so delta Q is the change in the temperature, as you heat something up, it has absorbed that much energy. So when your mother or father warms the kitchen, heats up a kettle, right? The water inside is absorbing the heat at a certain rate. As all of you know, different substances have different heat capacities. Metal has the greatest heat capacity, and what we call is this box, right, called a calorimeter. Okay, there is a wooden jacket inside, which with insulating material like wool, which is kept. Okay, there is a inside that you put a metallic container. Okay, then you put a thermometer into that metallic container, and that is called a calorimeter. A calorimeter is to precisely measure the heat content. Okay, now the term calorie is, of course, also today used um, um, food, right? It's used in healthcare and in food, right? Now, but calorie originally originates in the world of heat. Okay, so when a hot body is in contact with a cold body in an isolated container, the heat lost by the hot body is gained by the cold body. Okay, so what is this thing called heat? We will understand it when we go on to discuss the kinetic theory. We already discussed these examples. Delta Q equals ms delta theta. Gold sphere of 0.1 space for sufficient time in a vessel. So we discussed this, right? We discussed how when you do these problems, heat lost is equal to heat gained. This is a very central equation that you must know. Ms delta theta 1 plus ms delta theta 2, right? Initial heat equals final heat. What heat this guy has lost is gained by that guy. So that is the basic idea there. Now we are going to next discuss this change of state. Now, as you all know, right, when you boil a kettle, right, and I'm teaching this in very simple form, so you do understand what these things. You may already have seen it in your previous classes, but let me quickly explain this in simple form, because one must get the basics right. When something changes state from, say, solid to liquid, like when there is ice and it melts, or when there is even a metal which at a top at a very high temperature does melt, right? What happens to it is the metal itself goes from a solid state, and when we look at say van der Waals forces, etc., in the modern physics class, you will understand it at the atomic level. But at the physical level, what happens is it gets converted to a liquid, and in a liquid, molecules have more ability to move around. The molecules actually move around. In a solid state, the molecules are set. They sit in one place, and they sit in one place forever. If there is, why do metals have electrons move? Only the electrons move. The protons are set in metals or in any solid substance. They sit in one place, right? But in a liquid, things move around. If there are ions, they will move around. So now that moving around is actually temperature, related to the temperature. Okay? So now when you melt something, right, it has the temperature will not change for a long time, even as it gets converted from one state of from one state to another. For instance, if when ice melts, right, at 0 degrees, when ice melts, it becomes liquid. But then you still have to transfer a significant amount of heat to the ice to make it liquid. When water is boiled, it becomes water vapor, right? At that boiling point, when you see all those bubbles coming, right, it's transferring from one state, which is the liquid state, to the gaseous state. Now, in gases, the molecules move around much faster. Okay, So that added energy is provided by the process of heating the kettle. Okay, so the heat from by burning, say your natural gas, right? What do you call it? LNG, right? Or you know, so when you burn that natural gas, cooking gas, right? Cooking gas, typically the smell that you get in cooking gas is because of this thing called a mercaptan, you know. Now, so but mainly it is like, you know, methane, ethane, or propane. These are the gases they typically use when they, you know, in the US particularly, they use some amount of, you know, certain type of propane is used. Otherwise, there is methane and ethane. You know, all these are, you know, alkanes are used in most of these LPG type of things. You know, so so when you have these alkenes, which are gases burnt, right? Um, they then become, you know, you have CH4 plus, they become CO2, right? So on burning, so it's a chemical reaction which takes place, which releases energy, you know, and that energy is transferred to the metal, and from the metal it goes into the water, you know. And then at a certain temperature the water starts to boil, and then it gains the latent heat, okay, at that same temperature. So water will completely convert to gas, water vapor, okay, and therefore it will become H2O gas, right? And then yeah, the normal atmosphere, as many of you know, if people say it's very humid, it means that the amount of H2O gas is much more, right? So that is the basic idea here. Okay, so now that is the at that point, right? You have what is going on is called vaporization. The temperature at which liquid and vapor coexist in equilibrium is known as the boiling point. Now, the boiling point will change based on the pressure. Okay, if you put high pressure, you can increase the boiling. You can make boiling happen earlier. Remember, PV equals nRT, right? So now the so typically the sometimes you can also go from solid to vapor, and that is known as sublimation. Okay, so you go from solid to vapor, and this sometimes happens also in and there is a meeting point where all three of these can coexist, you know, and this is best described by what is called a phase diagram. A phase diagram provides a link between the pressure and the temperature. You know, it's a curve between the pressure. The higher the pressure, the lower the temperature at which you, so you can see these are upward sloping curves, right? So if the typically you can coexist at different temperatures, by pressuring something, you can make it become gaseous, etc. Okay, so or you can make it liquid. Okay, so you can make something liquid easier, you know, by putting a lot of pressure. Okay, so like for instance, under normal circumstances, the critical temperature may be here, under no, but then if you put more pressure, you can then change the temperature at which it happens. Okay, so so this is the P versus T curve in terms of phase diagram. Okay, so now uh, the liquid phase is here, you know, the vapor phase is here. Okay, and so the solid phase is here. Things exist as solids at lower temperatures, you know, and then they become liquids. So at a given temperature, like the normal temperature and pressure, which is the surrounding temperature of the atmosphere, which also changes, right? So at normal temperature and pressure, you can see that something will, in the normal case, will go from solid to liquid to gas, right? But then when you compress it, that point at which those things happen change. Okay, so then you have different types of material which has a different curve. Now, when things go from solid to gas directly, we say it is sublimation. Okay, when they go from liquid to vapor, we say it is vaporization. Okay, now this is what, this is going from solid to liquid, is melting, right? So these are the three phase transitions that happen. Okay, so now latent heat, as opposed to latent heat capacity, as opposed to specific heat, latent heat is what comes into play when you go from one state to another, right? When you go from one state to another, it is at a fixed, assume that the pressure is fixed. Okay, so now you're transferring, let's say you have given mass, right? You have, what is the, for per unit mass, how much heat do I have to give to transfer it from a particular state to the next state? That is to go from solid to liquid. Okay, so latent heat of vaporization is to take something from liquid to gas. So M times LV is how much heat it will take to, say, boil water. Okay, M times LV, where LV is the latent heat of vaporization of water. A very simple equation, but all the water will then convert at that particular, when you reach that particular temperature. Okay, before that you have ms theta. At this point you have ml. Okay, so no, keep that in mind. Okay, so when quantity of ice of 0 degrees, same story with, also with so this latent heat of in heat transfer. Okay, a quantity of ice at 0 degrees mixed with 0.5 kg of water at 40 degrees. The resulting temperature is 8 degrees. Calculate the heat of fusion, and he gives you the heat of the specific capacity of water, right? So now, what is the heat lost by the water? 32 degrees, delta theta is 32, 32 times 0.5 times 4186, right? So the water has lost that much heat, right? ms delta theta, right? Now that heat has gone to the ice, right? So now first the ice has melted 0.5 kg of ice, a certain kg of ice is, let's say it is M, right? M is, some amount, right? M times um, 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 3.34 times 10 to the power of 5, right? M times LF is the heat required to melt the ice, right? So now the heat required to melt the ice is M times LF, and the heat required to raise the ice from 0 to 8 is 8 times 8 degree ms delta theta, right? So M times 4186 times 8, and therefore heat loss equals heat gained. When you equate the two, you end up with finding out how much, the weight of the ice. So actually, that is the real question. He's not asking you the question as to what is the heat of fusion. Okay, so now conduction of heat happens when a body has one part hot and another part colder. So heat transmits from higher temperature to a lower temperature, right? Now conduction is what happens. Metals, just like they are very good conductors of electricity, because of the free flowing electrons, are also very good conductors of heat. Okay, so how does heat get transferred in a conductor? Is in a like for instance metal is that it gets transferred uh, molecule by molecule. Okay, this molecule, next molecule, and it goes very fast because the molecules, it is a kind of, think of heat as a kind of vibration which gets transferred, and it gets transferred quite fast. That's why when you heat something, you touch it, immediately you feel it as a in your finger, right? So please do not try that at home, right? So now we have the heat conductivity, right, is proportionate to the difference in temperature, right? So and the constant there is called thermal conductivity, K, right? Now the heat conductivity is also proportional to the area cross section, right? So if you had a very thin wire, just like in the case of resistance, also the greater the you may remember rho L by A, right? In the case of resistance, this is also very similar, right? Ka by L. Longer the length, wider the area, faster it will flow. Longer the length, also, so that is the idea there. Heat conductivity means how quickly the temperature leads to difference, leads to transmission. Okay, so now let's look at this example. An iron chain and a gold pendant are melded together. This is the time of Dhanteras. Everybody is buying gold, right? So, iron chain and a gold pendant melded together. The iron chain is at 400 Kelvin. The pendant is at 300 Kelvin. Okay, so now 273 Kelvin is 0 degrees, right? So 300 Kelvin is 27 degrees. 400 Kelvin is 133 degrees centigrade. What is the temperature at the junction of the two, right? Now, heat lost is Ka Ti minus Tc, right? Tc is the temperature at the junction. Okay, so K1A1 Ti is iron minus Tc, right, divided by L1, okay, will equal K2A2 Tg minus Tc by L2. Okay, so notice that the and eventually what we do is we say heat loss is equal to heat gained, right? So and there is a continuous flow of heat from one side to another. Okay, so how much heat flows from one side to another is dictated by this K, which is the thermal conductivity of each of these two. Okay, now so the temperature at the junction can be determined by solving these equations. Okay, so Tc is the common temperature at the junction, Ti is the temperature at which this one is, Tg is the temperature at which that one is, and the rate of flow is determined by the common temperature, right? So so K1A1 delta T by L. Okay, remember that. Okay, so convection happens to the actual movement of liquids and gases. When you have a liquid or a gas, right, the molecules themselves move around. Liquids, when they are heated, the liquid itself will move up. Okay, so let's say you heat a vessel, the liquid itself will move up and there will be currents inside the liquid. Okay, water vapor also moves up. When you heat water, as it heats up, it will move up. Okay, so there are what are called air currents which flow both into the land and away from the land. During the daytime, the earth is heated much quicker than the water. Okay, water Earth heats faster, and then therefore the air above the Earth becomes warmer. Okay, the air above the water is not as warm. Okay, so as a result, there is a flow of air from one side to the other. Okay, so at lower altitudes, air currents flow inwards to land during the day. Okay, so you will have this cool breeze coming in at 3 p.m. I'm sure all of you have felt it. Let's say you live in Mumbai or Visakhapatnam or Calicut or Chennai in the afternoon, or Goa in the afternoon, you will get some cool breeze, and so air currents flow inward from land during the day and outwards during the night. Okay, now the Earth's rotation also a little bit modifies these currents. Okay, now air descends at 30 degrees and then returns to the equator. That is called a trade wind. All these atmospheric are very much part of like meteorology. You have to learn all this atmospherics when you when you want to understand such a complicated field. It's a very complicated field. Anyway, but when infrared light or other light are transmitted across distance, it is called radiation. Infrared light is the means through which the sun heats our bodies. When you go and stand in the sun, you experience heat. That comes not from the visible side. That comes from the infrared. A red hot lamp or red hot iron also exhibits thermal radiation in addition to light. See, I'm looking at this light. This light also transmits some amount of infrared possibly, right? And you want to reduce that. You don't want to use a bulb for heating you up. You want the bulb to produce light only, right? So that is also part of the things that you have to understand. So now we now come to what is called black body radiation or Stefan Boltzmann's law. Stefan Boltzmann's law states that the heat radiated by a black body is a fixed body, which is existing in space somewhere. Okay, and so, like for instance, the sun can be treated as often as a black body. Okay, so what he said was the area over which the surface area of the body, right, times the it is proportional to the surface area of the body times the fourth power of the temperature, fourth power of the absolute temperature, not any temperature, absolute temperature, not a temperature difference. No, the body will naturally radiate heat at that temperature. So it is proportional to the surface area, as well as the fourth power of the temperature. Okay. So this is for a perfect black body. For an imperfect body, you therefore have an E. So there is a constant E as well, which is used for imperfect black body. That is tungsten 0.4. Why do they discuss tungsten so much? Because you use it in the bulb. Of course, today everyone is supposed to not use tungsten. More bulbs are used. LEDs are much more efficient because of this. But there's no heat issue, and also they are much more efficient in the use of conversion of the electrical energy into heat energy, into light energy. Sorry, they convert electrical energy into light energy. So so that's why they use these LED bulbs. So now AE sigma T to the power of 4. Okay. So now let's say there is a surrounding temperature Ts. Then the amount of heat transferred from the black body to the surrounding ambient, to a second surrounding temperature, is T to the power of 4 minus Ts to the power of 4. Okay, so it is proportional to the fourth power of the temperature. So this is with respect to radiative heat. Okay. Then we'll have a quick look at greenhouse effect. See, why does greenhouse effect happen? It is because of the latent ability of CO2 to absorb heat. Okay. See, the Earth's atmosphere consists of many gases. The most common gas in the Earth's atmosphere is nitrogen, you know, but there is also oxygen, and then there is also carbon dioxide. Okay. Now, nitrogen is a very inert material, but carbon dioxide, on the other hand, has the ability, along with other uh, greenhouse gases like methane, nitrous oxide, and various chlorofluorocarbons, to absorb a lot of heat. Okay. So now, as you know, the sun heats up the earth. The sun is a black body, sigma T to the power of 4, Stephen Boltzmann's law. It is always putting out heat, which is being absorbed by the earth, although the earth is so far away. It gives you an idea of how much heat the sun produces, how much light, of course, also produces, right? It's a huge fusion reactor. Okay. So that is the reason that you have to understand this material, this idea. Okay. So according to Arrhenius, okay, Arrhenius was a great grand uncle of this girl called Greta Thunberg. You may have heard of Greta Thunberg, right? So Arrhenius was a great grand uncle. He was one of the first people to actually propose this idea of the greenhouse effect. So now the Earth absorbs energy from the sun, which radiates tremendous heat and light. Okay. Now that heat and light, the light, just you all know, right? Light is also absorbed. If you I'm sure you know what absorbs light, right, and converts it to another form of energy. Plants, right? Of course, the solar panel and everything else, right? So plants absorb light, but heat is absorbed by very many things, including the CO2 and methane in the atmosphere, right? So now, when these things, they absorb heat, what happens to them? They start moving around. We'll discuss that when we go to kinetic theory of gases. They move around like that. Okay. This ends up. So what happens is, what heat is coming in is not going out. Okay. So it just comes in, it gets absorbed, and it sits in our atmosphere. Otherwise, it will just get hit and it will go away. Okay. So the greater the CO2, the idea is that because of the presence of CO2 in the atmosphere, there is this slow absorption of latent heat by that CO2, and then it keeps vibrating, and moving around. But no one really fully understands this whole process, and so it then eventually heats up the Earth's surface. Most of the heat that is coming into the Earth's atmosphere, right? Some of it is absorbed by the CO2, and some of it is the CO2 that is being released as part of this process. The CO2 itself, some of it is absorbed by the oceans. Okay, so the oceans, they absorb some of the CO2, and only a remnant remains in the atmosphere. That remnant, the theory goes, is absorbing more of the heat. Okay, because of its heat capacity, right, is higher, and therefore it has more ability to absorb heat, right? Remember, if you want to make some CO2, you have to get some oxygen from somewhere else. or water from somewhere else, right? So because that only has oxygen, so you have to take the H2O, or you have to take the O2, and you have to burn and then make CO2. Okay. So the theory goes that as the result of more and more burning of fossil fuels, right, like coal, right, kala patthar, right, kala patthar is black gold, right, coal, and of course oil, right, how all the cars and planes and buses and everything else, they all run on oil. In the US, they burn oil also for heat, to heat up the homes in the winter. So a lot of the last 150 years, we have been last almost 200 years, we've been big users of fossil fuels, and the amount of fossil fuel use has grown at an exponential rate. And so the result has been that there is more CO2 in the atmosphere. CO2 in the atmosphere has gone from 290 parts per million to almost 420 parts per million today. The theory goes that the ice caps can melt and sea level can rise if there is more and more CO2 in the atmosphere, and it absorbs all the infrared radiation being put out by the sun. So that is the idea behind the greenhouse effect, first proposed by Arrhenius, the grandfather of um, um, Greta Thunberg. So before instead of wasting your time some more, let me quickly go over Newton's law of cooling. dQ by dt is proportional to K times T minus Ts, where T is the heat of the body, and Ts is the surrounding temperature. Assume that the surrounding temperature stays constant, that the body alone is changing, right? Remember that in calorimetry, may not be the case, because you have completely isolated the situation. So dq by dt equals kt, right? That is the thing. So, and dq equals ms d theta. So ms d theta by T minus Ts equals K dt, and if you integrate dt by T, it is ln T, right? Therefore, Ms ln T equals Kt plus C. Please remember this equation. Remember, please understand this derivation. Okay, let me go over it very quickly one more time. Okay, dq by dt, rate of loss of heat, right? Remember, uh, uh, the rate of loss of heat means loss means it's negative, right? So K ms T is proportional to K times T minus Ts. This is Newton's law of cooling. Rate of loss of heat is proportional to the difference in temperature between the body and the surrounding. So notice, right, that the loss of ms dt, right, for a, let's say it's a hot body, right, the ms dt represents the heat, loss of heat, right? Ms d theta equals dq. We already discussed where S is the specific heat capacity, right? We already discussed this. Ms d theta by, therefore, theta minus theta s, or T minus Ts, Ms dt by T minus Ts, where capital T is the temperature and little t is the time, equals K dt. dt is the rate, right? So Ms, and so when you integrate both sides, on the right hand side, K dt will become Kt, because it's only time, right? K times T, K is a constant, right? On the left hand side, you have dt by T minus Ts. When you integrate dt by T, it is ln T. Okay, integral dt by T is ln T. Therefore, you have ln T minus Ts. Ms ln T minus Ts equals Kt plus C. Now, in the initial conditions, when you apply the initial conditions, you end up with a value for the constant. So at in the initial temperature T naught, this will become T naught. Time will be 0 at time t equals 0. This is T naught, right? Therefore, you have C equals ms ln T naught minus Ts. Okay, therefore you will have this equation. Now, if you rewrite this equation without the ln, right? If ln x equals y, e to the y equals x, right? So when you rewrite the equation in this form, you will end up with this kind of e to the y equation, and when you solve the boundary conditions. But this derivation is a very critical derivation. You may get some problems definitely using Newton's law of cooling. Very simple, but still it's worth not missing out on the marks. Okay, so an oven cools from 90 to 80 in 2 minutes. The room temperature is at 25 degrees. How long will it take to cool from 80 to 70? See, remember Newton's law, right? Newton's law states that the rate of loss of heat is proportional to the difference in temperature. So if it takes 2 minutes and you want to, you can't say it will take another 2 minutes to go from 80 to 70 also. No, it will take more time to go from 35 to 25. It will take the longest time. Okay, so eventually it will go down to 25, right? So the oven is finally going to sit at 25, right? That's going to be the long-term thing, but it is going to be a exponentially decaying curve. Okay, so if you plug in this equation, or you derive this equation and plug it from here, you will get the same answer. Okay, that's what he is saying. Okay, so now ms dt by t minus ts equals kt. When you integrate, the other way of solving this is using this equation that he's saying. So you look at the average temperature and then you use that. Okay, now I have run out of time and I have to close today, but I will be returning to this particular matter in the next class when I relook at Newton's Newton's law of cooling. I'll quickly go over this and then I will continue. But in the meanwhile, if you can please do some problems involving thermal properties of matter and download our app and then use the assessment module there, that would be very good. Please go to com.jnanamarga.ramanujan, com.jnanamarga.sushruta, download our app and and try some questions. All right, I'll see you again next class. Until then, have a wonderful weekend and happy Diwali again to all of you students.